All right, so first thing you'll notice is a note. Solve the differential equation means to find the general solution, right? So for instance, if you have y prime equals ky, we've done this before. This means you took the derivative of something and you got the same thing back, but times a constant. So e to the kx would do it, right? We're thinking y would be that. But that would be a particular solution, right? Because we also talked about in class that this times any constant, c, would also satisfy it. We've done this before. We're going to get into this more today, but this is what they mean. This would be, so if I said solve the differential equation, this would be the solution, because this would be a family of solutions for different values of c, right? So that's what they mean by that. That's like 1 through 10 or something like that. It just says solve the differential equation. And so what they're looking for is the general solution there, which is a family of functions. Okay, now, homework 42, page 622, section 10.3, number 1 through 21 odd, 29, 31, 35. And what did I wanted to say? Yeah, 35. In 35, it says in exercise 13 in section 10.1, we formulated a model, blah, 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 blah. I don't think we saw that. You might want to just go back and look at what that is, exercise 13 in 10.1, just so, like, it'll have a bit more meaning to you if you know what this is a model of, rather than just plugging it in and chugging, and you could do that. But it might be more interesting to you if you know what that differential equation is. So, okay, here we go. This is a table of data. Let's explain what this is. So what you did is, let's say it's a pot of water. You put a pot of water on the stove and you boiled it. And once it started boiling, you take it off the stove and you stick a thermometer in there and you hit a timer. First thing you note is that at time 0, it's 100 degrees Celsius. And so this is what you're doing. You're taking time in minutes and temperature, capital T, in degrees Celsius. So here your first data point is that at time 0, when you started your watch, it was 100.000 Celsius. Then after 1 minute, you wait a minute and then you check the temperature again and you see that it's 52.591 degrees Celsius. And so on after 2 minutes, after 3 minutes, after 4 minutes, and you get this sequence of numbers. And so you take your table of data and you go, okay, let's graph this and see what's going on. And so you graph it. Here as our input we have time in minutes, and my output is temperature, capital T, in degrees Celsius. And it looks something like this. First question. So it looks like this is approaching some value. What value is it approaching?
25.
It looks like 25 degrees Celsius. What do you think that might be?
Room temp.
Yeah, right? It makes sense that you have something that's hot, and over time, it's going to equilibrate with its surroundings, right? And so, yes, indeed, you look at your data and you go, oh yeah, that's right, and you happen to have some more data, which, because whatever. You look and you say, yes, indeed, the room temperature was 25 at that time. And so we're going to give that, for what we're going to do, we're going to give that a special variable name. It's not a variable. We're going to give that a special constant name. T0. Has nothing to do with time 0. This is just the way that this is always done. Sometimes you'll see it as T sur, means the temperature of the surroundings. But I think in our book they use 0. It means the same thing. It's the temperature of the surroundings. And it's annoying that they use 0 because of course every other time we're going to use 0, that's going to correspond to what it is at time 0, or the initial thing. Obviously that's not the initial temperature. The initial temperature was this. This is just what they do. And so I'm going to stick with the way the book does it. They might have a t sub s. I don't remember because it's not. I don't think it's actually in this section. But whatever, right? I want to do this. So this is the surrounding temperature, the ambient temperature, the room temperature, the temperature of the surroundings. And yes, indeed, your data does do what you expect. That over time, as time goes on, the temperature of your, I guess, pot of water or piece of steel, whatever it is, does approach room temperature as you expect it to. Okay, cool. Here's the question. We want to model this. We want a function, t of t, confusingly, right? T of t. Big T, in other words, degrees Celsius. This should give you degrees Celsius. The output of this function should be degrees Celsius given some input little t time in minutes, right? That's what we want. And there are about 1,000,000,001 ways of doing this. What kind of function does this look like to you?
Root x. Okay.
Could be. I mean, it kind of, so I know that, like, if this is t, root t is kind of like this, square root t. And so maybe this is some kind of negative square root t that's been shifted up to 100. Maybe this is like, and so it does something like this. You might guess that the function that we're dealing with is some kind of 100 minus root t or something like that, or some constant. The problem with root t, though, is the square root is going to continue to climb forever. It never hits an asymptote, right? But maybe in this range here, this is a very good approximation for that. In fact, it might be able to hit this perfectly. It might be able to hit all of those data points if we do this with some kind of, I don't know, k and maybe at plus b or something like that. I don't know. It might work perfectly. But there's another kind of function that does this kind of decay thing. What function do you know comes down and flattens out and approaches an asymptote? E to the x. Or also, but maybe how about 1 over t?
Oh, yeah.
That might do it. It might just be that it's been shifted because, like, obviously the temperature isn't, if you go back in time, the temperature didn't explode. But maybe if we take 1 over t and shift it a little bit and then put it up by 25, right? So maybe we go 1 over t to shift it that way would be plus some number n, and then add 25, and we would have the function 1 over t shifted sufficiently over and then shifted up, and maybe that thing right there approximates our function very, very well. Maybe it's something different than that. Maybe, who knows, if we took more data points here. So right now we have this. We have a data point here. We have a data point, like, I'm going to exaggerate it here, and then some down here. Maybe if we took more data points in between here, we'd find that it does something like this. Maybe it's flat for a little while and then starts to go down. In which case, maybe this thing is better approximated by something like this, with maybe 100 on the top. Maybe this is some k, and maybe this is some a, I don't know. Maybe that's the type of function that we want to fit to this. Maybe, like you said, exponential. Exponential might work too, right? Because we know an exponential function, a decay, right? E to the kt. If k is a negative number, it's going to look like that, right? So something like e to the negative 2t would look something like this. And then maybe we take that and shift him up by 25. And maybe that's a good one. But the question is, like, we could, and I'm telling, or maybe we use a polynomial. Maybe this is like part of some polynomial that, I don't know, does this, and then it comes up and does something like that. But right here in this range where our data points are, it fits perfectly. And so then the question becomes, okay, well, which one do we want? And how can we select which is the best? Because I can tell you right now, given 10 data points, I could derive a polynomial that hits each one of them exactly and is nice and smooth between each one. And so then it's like, well, is that what we want? And this process that we're looking for is called curve fitting. You have some data and you want to interpolate. Interpolate means to find bits between your data points. Extrapolate would be figure out what's going on outside of your data points. But right now, we're interested in interpolating between here. What function fits this data the best? And maybe we're also interested in extrapolating to figure out what happens as time goes on. If I have this, maybe can I predict what's going to happen at 12 minutes, at 20 minutes, you know, but whatever. This process is called curve fitting. And in general, there are infinitely many different curves we could fit to this data. And there are infinitely many curves that we can make it fit exactly. So then the question is, okay, what do we do? How do we narrow this down? And that's a whole field of mathematics that you could explore if you want. But one way that we could try to get a hang of what's going on here, and this may very well be the first thing you try anytime you have, or one of the first, it depends, but definitely with some kind of data set like this, you would say, well, one thing that would be nice is that if I could get a differential equation out of this, if I could somehow turn this data into a differential equation, something like t prime equals some function involving t, then I could solve and get an actual function t, the thing that I'm looking for. Right? That's the idea here. And then in that sense, we could say that the function which satisfies this differential equation is, in a sense, in one sense, the best fit for this. Because if the derivative determines where a function goes, and we have some kind of differential equation involving, I shouldn't have erased this, some differential equation involving t. And notice, there's a lot of different ways that differential equations could go, right? Like you might have t double prime plus t prime minus 2t equals 0. Okay, that's cool and all, but it would be really nice if we could get it so that there's no second derivatives. So in other words, if we don't know this just by looking at the data, but if we could turn this into just a t prime by itself, and then get all my other t's on the other side, life is going to be much, much, much easier for us. So that's the direction we're going to go. It may be that doing what we're about to do, gives you a differential equation that's way harder than the thing that you're working on. But it might be that doing what we're about to do makes your life easier. And if that's the case, it's a very good way to proceed. So what we're going to do, so again, I'm thinking, okay, if I could get some kind of relationship, dt equals something, I don't know what it is, but it involves t, then I could use what I know about differential equations to find a solution, capital T, of little t. In other words, some solution which is a function of temperature given some time. But in order to do that, I don't have any dt's. And this is all, right now, these are all just points here. I don't have a function that I could take a derivative of, but I could approximate it, right? Because dt is the change in t divided by the change in little t, right? So in other words, here we go, let's just look at this. If I think about the change in big T from here to here, this would be my change in big T. And this right here would be my change in little t. So I could say in this case, right here, the first bit, dt, or delta big T, delta little t, would be 100 minus that number, right? So 100 minus 52.591 all over 1 minus 0. Oh, that's nice. Oh, look at that. Every one of these is going to be 1. Oh, it's almost like you knew ahead of time what was going to make your data easier to deal with, and you decided, I'm gonna take equally spaced data. That'll make my life easier. And if I make it all 1, that'll be nice. And so what you end up getting is negative 47. Negative 47.409 for that bit right there. And we could say, okay, well then we'll understand that we don't have a perfect continuous function here that we took a derivative of. But we didn't have a perfect continuous function at the beginning, so we'll just say that here, from time 0 to 1, the derivative of big T is equal to negative 47.409. Does that sound reasonable?
Yeah.
Sounds like a reasonable thing. So I'm going to add to my table right now. And in order to do that, I got to erase this data point. Sorry, we're going to do that. And say, okay, that first little bit right there. So now I'm keeping track of the derivative delta, or d temperature, d time. And we're going to say, okay, well, right around here, that slope is about negative 47.409. And then I do that for the next bit. I say, okay, here we go. We go from here to here. That's delta t. This from here to here is delta little t, which is, okay, delta big. So the slope in this area is about this one, or yes, the last minus that, so 28.734 minus, or wait, no, oh, I messed that up, didn't I? It's the one at 2 minus the one at 1. So 35.150 minus 52.591 all over 2 minus 1, which works out to negative 17.441. And so I'll add that. And then I'm just going to go ahead, and I think you get the idea of what we're doing now. We're just going to go point-wise, each one of these guys, and say, okay, negative 17.441. Then I calculate the slope between the next two. And I get negative 6.416. Then I do it on the next one, and I get negative 2.36. And this makes sense, right? Because the slope is really negative at first. It's still negative, but it's getting smaller and smaller in magnitude each time. And so this is good. And I just did this in Python. I just plugged these numbers in and did some Python magic, and this is what I got. 869, that's negative 0.869. The one at 5 is negative 0.319. Then negative 0.043. The one, oh no, I'm sorry. Negative 0.118. The one at 7 is negative 0.043. The one at 8 is negative 0.016. And then I get at 9 negative 0.006. And and that's the last one I can compute, right? Just think about it. The one I was calling, the one at 0, I used this bit. The one that I'm calling at 1, I used this bit. The one at 2 was this, and so on. So the one at 9 uses this right here, and I don't have another data point out here. I'm losing a data point, and so we don't have anything here. Now, if you've only taken 10 data points, losing one data point might mess your world up. It might affect everything that you're about to do. So if that's the case with this thing that you're modeling, you might want to go back and collect more data points. But usually, if you're doing something like this, you have about 100,000 of these points. And so losing one it's not going to matter. You want to make sure that that's the case for what you're doing, okay? Okay, now, here's the thing, and this is, the thing that you want to do is not the thing that you should do here. The thing that you want to do is the following. The thing that your brain tells you to do is to graph dt versus t. Because that's what you want. I don't know why. This is just what your brain tells you to do. It says, okay, do this. And I did the thing, didn't I? I did the thing. I knew I was going to do that thing. Your brain tells you, okay, I'm going to graph this stuff. So I'm going to graph the derivative. I'm going to graph the slope given some time. So at 0, you're at negative 47. At 1, you're at negative 17. At 2, you're at negative 6. And so on and so forth, and you end up getting something that looks like this. And you're like, can I get a function for this with t? But now you're kind of back in the same situation, right? It's like, well, just like we started off with, it's like, which function fits this best? Like you have infinitely many possibilities. And maybe, actually, maybe not. Maybe you do this, and you're like, I know exactly what function that is. And it works, and it's true. But when you just have a bunch of points, there's no guarantee, unless you have other information about your data, there's no guarantee that the function that you come up with is going to help. But remember, this isn't what we wanted. This isn't going to give you a differential equation. Best case scenario, this gives you something like this. dt equals, I don't know, root t minus 47. Then you could integrate it, and then you'd have your function. But I'm telling you right now, that's not what this is. This is not even close. And so that would be best case scenario, that you do get an actual function out of this. But that's not what we want. We want dt equals something in terms of big T. So the thing that we want to graph is not time versus the derivative. We want t versus the derivative. That's the thing we want to get right now. Because if we could think, because remember, a differential equation, in fact, one of the best ones you could get, would be some kind of function here involving big T. Because if that's the case, then you have a differential equation. If little t is in there, I mean, if you try it, and like we just did, you do this and you find your points, and hey, I know exactly what function that is, well then, good to go. I didn't know what function that was. I could take a guess, but it's not going to help me. So the thing I'm graphing now, and this is just like or like when you're trying to figure out a slope field, right? And you have some differential equation, f prime equals, I don't know, 2f. Then you graph f versus f prime, and you find, okay, it's 0, bigger, bigger, negative, negative, and then you get a slope field, right? This is kind of like the same thing that we're doing here, right? We're saying, well, let's look at the input, let's make our input value the actual function that we want, and our output value will be the derivative of that function. Hopefully it's a function we recognize, and then we'll be able to get this, which is our goal. Get a differential equation with dt's on one side and t's on the other side. In other words, we want the slope as a function of the function itself. So the thing we're going to graph now is going to be dt versus big T. And so, when big T is 100, I get out a negative 47. .409, right? Now here's something. I could just go through, step back and do all of these. I want to take a look at this last point that we have though. This says when big T is 25.009. Okay, so 25.009. Then my derivative, the output, is really close to here. Negative 0.006. Okay. Now I step forward a little bit to 20, where big T, my new input, is 25.025, and I get this guy is negative 0.016. 0.016. You get what I'm doing?
Yes.
Okay, I keep doing that, and I keep doing that with all of these. It's weird because it used to be 0 was over here, but now it's getting a little weird. But you do that, and something crazy happens. If you actually do this, like let's say you have these values in Python, and you just say, forget about this graph, this is my input, this is my output, it will give you this. It looks like a straight line. It really looks like a straight line. And so what you do is you go, wait a second. If that's a straight, let's just see. And so you do a little bit more investigating. You say, is this indeed a straight line? If it is, then every time I calculate the slope between these guys, I do my rise and my run. I do my rise and my run. I do my rise and my run. Every single one of these times, I should get the exact same thing. In a perfect world where I had exact numbers here. But I know that I don't have exact numbers because, well, obviously my thermometer only measured out to the thousandths place. Also, I'm pretty sure I didn't do this at exactly 2 minutes. In the real world, I didn't. I tried my best to get it at 2.000000, but I was probably off by a little bit. So I actually, given that there's a little bit of uncertainty in the measurements, I should expect that the slope each time is going to be a little bit different. If it were exactly the same, I would be a little suspicious, right? Yeah. So what I'm going to do is figure out the slope for each one of these. And I'm going to call, instead of calling it m, I'm going to call it k. I'm going to say, okay then, the slope right here, I'm going to call it k0 because it's the 0th one. And I'm going to calculate it. And so I take my rise over my run, which is that over that. I tell Python to do it because I don't do it myself, but you do that, and it actually, if you were to do it by hand, you'd have negative point. Oh, well, that's why it came out weird, because I used the wrong data points. Interesting. Anyway, so see, I did it wrong when I did it by hand, and then I told Python to do it, and I was like, huh, I got something different there. Anyway, who cares? Negative point, what this works out to be is negative 0.625. Then you compute the next one, and we'll call it K1. And what you get is negative 0.628. Ooh, that's cool. K2, which is this one right here, the rise over the run, gives you negative 0.636. Okay, all right, okay. And so you keep going, and I'm just going to actually write down what each of them are. K0, we got negative 0.625. K1 was negative 0.628. K2, negative 0.636. K3, negative 0.630. K4, negative 0.633. K5, negative 0.632. K6, negative 0.632. K7, negative 0.632. And K8, negative 0.632. So the slope, as far as we're concerned, is constant. Let's take a look at a couple things to notice here. When the values here are really small, we're using really small values, look at this. We have a 0, 0, 0, 6. 0, 0, 1, 6. We have one significant digit there. That's the only digit that has meaning, or has that has value, that gives us data. Everything else is just kind of thrown away. However, when you're up here, you have 1, 2, 3, 4, 5 significant digits. Here, 5. Here, 4. Here, 3. There are more, I just didn't write them down. Here's 3, 3, 3, 2, 2, 1. We're kind of throwing data away when these are really small. It's, in a sense, we're throwing data away. We can't trust anything past here, right? Because my measurement was only so good. You can't trust anything past there. So it actually makes sense that when we're using these points with this data, we get something different than if we're using this. And look at this, 632, 632, 632, 632. When we have enough, when we have more data to compute these things, we get something consistent. So what we're seeing here is rounding error. We're seeing that we're kind of rounding off all of this stuff back there. And when you do that, you get stuff that's not exactly right. I mean, it's close, right? It's not that. But so anyway, okay. So what have we discovered? We plotted our points. We plotted t versus dt. T versus dt. I'm sorry. And what we end up with is as far as we're concerned, a straight line. And this is what I meant, like earlier, you might look at it and go, I know exactly what that is. This is one of those cases where you look at your data and go, I know exactly what that is. I feel convinced that this is all on one straight line. And I can figure out what that straight line is. I could say, okay, this is some straight line, y equals mx plus b. I know the slope. The slope, and what I'm going to do is say, you know what, it looks like it's getting more and more accurate. So I'm going to take this one. What you could do is take an average of all of these, and maybe you want to do that. Maybe in whatever application you're doing, that makes sense. I think it just looks to me like it's getting better and better as we get down here. Like this is probably the ground truth here. So what I'm going to say is that the slope of this thing, k, this is a line, and its slope, k, is equal to negative 0.632. That's what it looks like to me. Okay? I'm going to do one more thing. Because right now I'm thinking I want the equation of this line. Because if I get the equation of this line, y equals mx plus b, then I'll have that is what I'm going to use right here. Right? Output is that variable. Output is that variable. Input is this expression. I'll put that expression right here. It won't be an x, of course, and it won't be an m. It'll be my k. And I'll be able to plug and chug. Turns out, though, we could actually make this a lot simpler. Because in this case, what would b correspond to? I guess b would be, of course, you know that b is the y-intercept. And so that would mean that the temperature, T, is 0.
Stops at 25.
Yeah, and you know that it stops at 25. I mean, we can't guarantee that that has physical meaning. Like, when does the temperature 0? Well, it's not. It's not going to happen. So what we're going to do, so we're going to kill two birds with one stone here. We're going to make this a lot easier by saying, so also, we're going to just use our imaginations here. So I got my k. Remember, we got our k by doing these successive computations of the slope at all of our data points. So that's how we got our k. We decided that the k that we're going to use is that guy. Now let's just imagine here. Remember our original data set. Looked like this, and it came down, and it approached this value right here, which we call t0. Now I think it's a pretty reasonable assumption to say that this trend is going to continue. That as t goes on forever, he's going to approach t0. And so the bigger and bigger numbers that I put in here, this will get closer and closer to that line. And if that's the case, then those slopes, what's going to happen to those slopes in between each of those data points? What are they going to approach? They're going to approach 0. So what I'm saying here, so I want to keep this here. I want to keep this. Our goal is to get a dt equals some function of t, which now we know is going to be a linear function, which is what we want. It's the best case scenario. In order to get this, where my output is degrees Celsius. That's my goal. We'll have a differential equation, and its general solution will be some function, temperature as a function of time. That's what we want. So, but let's just think about this. As we go on, and as time gets bigger and bigger, and now we're at n, big old number n, and n plus 1, and so on, we think that this thing's going to get arbitrarily close to 25. Bunch of zeros, 25, 0, 0, 0, 0, 0, 0, 0. So what does that mean for the derivative? That derivative should also approach 0. You just said that, right?
Yeah.
That's what you're saying, that it's going to be negative, but it's going to get closer and closer to 0. So it's going to be approximately equal to 0 after some point. So if we were to graph that, as this thing gets closer and closer to 25, we have technically infinitely many data points which are going to get closer and closer here, right? That's what we're saying. We have infinitely many data points, which get closer and closer to 0 in this direction as t gets closer and closer to this value right here, which is 25. In other words, it's kind of like an asymptote right there. You think about it. Then there's your asymptote right there, right? T, this was when we graphed big T versus time. We had an asymptote. Well, it makes sense that there's an asymptote right here, and he can't go down past 25 because he can't go down past 25. And they're going to approach as you go this way. So what we're going to do is just be a little bit tricky here. We're going to say, well, hold on. If I just take this picture and shift him over to here, then the y-intercept will be 0. Let's do that. So let me re-record this. I have my k, which is negative 0.632. And I'm just going to take this and shift him over. Now here, this is where it gets really tricky. So I'm just taking each of these data points and I'm shifting them over. We have like infinitely many that do that. And then boom, 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 and boom, like that. Now, one way of doing that is to say, okay, this thing right here, this y was originally some function mx plus b, and I shifted him that way, so I guess I need to add to x, so he should be x plus 25 plus b, but now we know b is 0, so blah 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 blah. But that's how I would do it if I cared to do that. I don't care to do that. What I want to do is say, well, hold up. Let's just do it right here. Why don't I just subtract 25 off of each one of these points right here? Okay? So instead, and so that's what I'm going to do. I'm just going to subtract off 25 from each one of these. 25 minus 25 minus 25 minus 25, and so on all the way down to here, minus 25. And you can see, like, yeah, 25.0003. Oh wait, we don't have that one. 25 minus 0.0009 minus 25 is the 0.0009 that we had. And his output value was this guy right there. So I'm not graphing t versus its slope. I'm graphing t minus t0 versus its slope. In fact, we could just say that's what this input variable is now. He's not t. I don't want to get rid, I don't have room to write it here, but I would say, well, now this column, after I subtract off 25, he's t minus t0. That is what this column is. So that's the variable, the input variable that I'm putting into the function. We could do it the other way. And what we end up with is going to be exactly the same. It's just going to make my differential equation harder to solve. Knowing that this makes it easier to solve, I'm taking this route. But we could have taken the other route and we would end up at the same place. Just so you know. If this really bugs you what I just did, just know that you can do it your way and it'll all work out just fine. Okay. So now, finally, we say this green thing is a line. Therefore, it has the form y equals mx plus b. And we could say, but look at what the b is. The b is 0. So I'll just say this equation, or this line, has the form y equals mx. What's its slope?
Negative 0.6.
Yep. So it's k. Y equals k x, whatever we got for k. Now the x isn't x, the x is what?
T minus t0.
Okay, so that's k equals t minus t0, where t0 is just some constant. In fact, in our thing, it was just 25. Easy, okay. So, but I want to keep this more general. Now y, what is the output?
dt over
So the change in temperature with respect to time, lo and behold, we have the thing that we were looking for. We have a differential equation. On the right-hand side, we have nothing but big T, the function. On the left-hand side, we have nothing but its derivative. We have a differential equation. And indeed, this is the differential equation for cooling or heating. This is what it is. It says that the change in temperature with respect to time is proportional to the difference between the temperature of the object and the surrounding temperature. So the bigger the temperature difference between your pot of water and the surrounding area, the faster he's going to change.
Yeah, that makes sense.
Yeah. Now let's solve it. We have not talked about how to solve these things yet. I'm gonna get him. I'm gonna keep him here. We found dt is k t minus t0, where t0 is 25. Okay. All right. This differential equation is of a certain type, and it's called separable. It is a separable differential equation. It's actually a first-order linear separable differential equation. But what we're interested in now is the fact that it's separable. We're going to talk about what that is right now. Notice, by the way, this is empirically derived. This is not, we didn't think it should be the case that an object should cool, that at the rate that its temperature changes is proportional to, no. We derived this empirically,
Yeah.
right? We found that this was true. We didn't go and reason this out. So this would be called an empirically derived one. Okay, but here we go. A separable differential equation is one of this form. dy dx is equal to some function of x times some function of y. Why is it called separable? Because you could separate them. Watch what happens. I could divide by the y's, multiply by dx. Now I have an expression that has nothing but y's on one side, nothing but x's on the other side. And now you could do this. Do you believe that you could do that?
Yeah.
Yeah, why not, right? This just says you have some function, you took the derivative of it, and that's what you got. This says you have some function, you took the derivative, and that's what you got. So just undo those derivatives. The problem happens when you're all mixed together, right? When they're mixed together like this, how do you undo that? Yes, it's true that I could take the integral with respect to x, okay, and I'll take the integral with respect to x, but what do you do about that? That is a function of x, right? But if you could separate them, then you get this. So here's an example of a separable differential equation. Y prime equals ky. And what's nice about Leibniz notation is it really helps you keep everything in order. In fact, this is the reason why I ever use Leibniz, is to do separable differential equations, because it helps you here. You go, wait a minute, hold up. Can I do this? Can I get all the y's on one side and all the x's on the other? Yeah, let me just bring this y down. Over y equals k, and I'll bring all my x's over here. Now there doesn't happen to be an explicit x over here, but that's cool. We don't need to have an x show up in there. Okay? Now let's integrate both sides. Integrate over here, integrate over here. What's the antiderivative of 1 over y with respect to y?
Natural.
natural log of y, right? So natural log of y plus some constant, right? Okay. Now, what's the antiderivative of some constant with respect to x?
kx.
Kx plus some other constant. It's called C2. Now the whole point of this is to get, I want, what I'm looking for, my goal, I want to get a y of x. So we need to get the y by itself. So what I'm going to do is I'm going to say, okay, log y is equal to kx plus c2 minus c1. But if those are both constants, c2 minus c1 itself is a constant, right? So I'm just going to rewrite that as some new constant, kx plus, let's call it c3. Does that make sense?
Yes.
Okay. Remember, these are just the constants that come. And remember, it could be anything. And it will still be true. Add any number to log y, and when you take the derivative of it with respect to y, you will get 1 over y. That's all that's saying, right? Okay, okay. So now how do I get y by itself? What do I have to do?
E to the natural log of y.
E. So I need to take both sides up to the e. That makes the y pop out. This gives me e to the kx plus c3. Now we could leave it like this, and we'd be good to go. But we could, it's actually be much easier for us if we split this guy up like this, kx times e to the c3. But c3 is just some constant, right? So e to a constant is just some constant, right? So I could rewrite this entire thing as some constant. And let's give that constant the name just plain old c. So this says that y equals some constant plain old c e to the kx, as we expected. Oh, that's cool. Because we weren't able to really prove it last time. We weren't able to, it's not that we've proven it, it's that we weren't able to derive it from first principles. We just kind of had to go, e, probably e, and then, well, what about, like, there's probably more than just that. Well, look what happened. And then I had to, like, bring c in out of nowhere. I was like, but look, if you multiply by 2, it still works. If you multiply by 3, so we had to reason that it's c. It's kind of nice to see where that thing comes from. Right? It comes from this, and the fact that we could rearrange it. You could have written it like this, and that would be a perfectly good solution, but this is a bit more useful. And so this is your general solution to that thing right there. Okay? Is this making sense?
Yes.
And remember, this is a function, y of x. It's always what you're looking for is a function. And yeah. Okay, so back to our original guy here, or our empirically derived differential equation. Actually, before we do that, let's look at a couple things here. df dx equals 3x squared y. Yeah, let's use y. So let's use it. Look really ugly. 3x squared y. Is that differential equation separable?
Yes.
Yeah, because again, right, we could get all the y's on one side. That's your only question here. The very first thing you ask yourself whenever you have a differential equation is, can I get all the y's on one side and all the x's on the other? If so, you're good to go. Okay? How about this? dy dx equals xy plus x.
Yeah. No. Well, you can't go.
Let's see. Hold up. Maybe. I'm not sure. X times y plus 1. It looks like it is, actually.
Oh, yeah.
Yeah, it looks like it is. Okay, so dy over y plus 1 equals x dx. Easy! Let me just integrate both sides. Nice. That's not bad. Well, but what about this? I bring the dx up, we have y plus x dx, y dx plus x dx dy. It's not looking too good. There's a way of dealing with it. If you do have something like this, there's a way of dealing with it, but we're not taking a class in differential equations. But this one, I would say, is not separable. Unless you make some kind of substitution, you have to be really creative about that. As it's written, this thing is not separable, and so you're going to need to use other methods to crack this guy. But the ones that we're going to see in this section, most likely, will all be separable. So, here's another one. Is this one separable? Okay. Now, there's another thing. I didn't really say this. You could, if you wanted. We had this dy, we used x, was ky. We could have solved this by doing this. Bring the k downstairs, and then just have the dx upstairs. And we'd end up with the same thing. It would look a little bit different, but you would end up with the same thing. If you're interested, prove that. Like, go ahead, continue on with this and show that we do get that y is equal to some constant e to the k x. You'll get the same thing. It's just that oftentimes constants, it's nice to keep them away from where your variables are, right? Or where your function is. And so this one is separable. dt over t minus t0 equals k t. Again, could bring the k over and everything would work out just fine. But that's not how we're going to do it. So now what do? We integrate both sides. What's that?
Natural log t minus t0.
There we go. T minus t0
Equals k to kt.
kt plus a constant. Now, what's one thing I didn't do? Because when you're doing differential equations, you just wait till the end. Because this is plus some c1, this is plus some c2, and you know you could absorb all of them over here to get a c2 minus c1, which you're going to give a different name anyway. And so each one of these steps that you take, you just wait till the end and put your constant there at the end. That's what you usually do. Now, how do we get the t by itself? E of both sides. E. That makes this guy pop out. T minus t0. And remember, the t is a t of t. And the t0 was just 25. So it's just a number. So we're just going to leave it like that. Now this is e to the kt plus c3, which we do this, we're going to play the same trick here. We're going to just keep absorbing everything into a constant that we can. This is just c3, and therefore this entire thing is a constant. E to the whatever c3 is just some constant. We're going to call it big C. So that gives us t of t minus t0 is equal to some constant times e to the kt. Almost there. I want him by himself, so we get t of t is equal to some constant e to the kt minus t0.
Would it be plus t0?
Plus. Thank you. Excellent. Good catch. Now, let's make it actually fit our data. So, I only introduced these variables to make my life easier, right? If we didn't think like, oh, I want a general solution for any k and any t0, we would have just left that as 25, and we would have left k as negative 0.632. So let's get these guys back in. We have t of t is equal to some constant, I don't know what it is, e to the negative 0.632t plus 25. Now let's find the particular solution. How do we do that? Because remember, this is now, and let's hold up for a second. And see what, because this is the general solution to our specific problem where we empirically found that K was negative 0.632 and where we were in a room where the ambient temperature was 25 degrees Celsius. So, what these things would look like, you can imagine if C is equal to 0, this is just the constant function 25. Right? This is when C is equal to 0. Probably not the case, but I guess this would be the thing that you took out of the oven was already at 25 degrees. So it just stayed at 25 degrees, right? Okay, now let's just think about families of functions. If C is equal to 1, then this thing would be, I guess he would go through here at 26, right? Because plug in a 0 for t 0 is C, we're saying that C is equal to 1. 1 times e to the 0 plus 25, yeah? Which is 1 plus 25 is 26. So he would start here at 26, and he would decay like this. Oops, sorry. Right? And so on and so forth. And we could imagine for different values, this was when C was equal to 1. We can imagine different values and so on and so forth. How do we get our specific one? This is an initial value problem. We just say, I know that at some time my output was some output. And we had 10 data points. We could use any one that we want. I would rather use that when my time in was 0, my output in degrees Celsius was 100. That's probably going to make my life easy here. And say, okay, I want the one where it's the situation that I was in. And so when I plugged in a 0, I got out a 100. That's the same thing as getting C e to the stuff times 0. Again, make your life a lot easier by using 0 in this case. That gives me 100 equals C times 0. I mean, e to the 0 is that, so it's just C 25. So 75 equals the C that I'm looking for. And so when C equal 75, that's the particular solution Six, 3, 2. That's the particular solution which describes my data. So there you go. That's the model right there. Now we could use it to predict, okay, what's going to happen in the future. What was it at time equals 0.5? That's a good question because, you know, it dropped in the first minute, it dropped from 100 down to 52. And then the question is like, well, what was it after 30 seconds at 0.5? Was it here in the middle? Was it down here? Where was it? Well, plug in 0.5 into there and figure it out. One more thing. What if we didn't have our initial data point? What if all we had was T, not T of 0, we knew that at time 1 the temperature was 52 point whatever it was. We could still figure this out. It's just gonna get ugly, right? We say, well, 52 point stuff is equal to T1. T1 is C e to the negative 0.632. So and even 1 is easier than, like, say 2 because we don't have to multiply T times that thing. It worked out nice. Plus 25 is 52. So 52 minus 25 is 27. So 27 equals C e to the negative 0.632. That's just a number. I could divide through and get 27 over e to the negative 0.632 is equal to c. And I'll bet that comes out to 75. And so, okay, so that's a separable differential equation. There's one more thing we need to talk about today, and it's really cool. I think this is cool, and not for any useful purpose whatsoever. Though there are tons of uses for what we're going to talk about, I didn't even bother writing them down, because I don't care. I think that this is just really cool. And I guess, just graphically, I think it's really cool. So check this out. Orthogonal trajectories. So given a family of curves, notice I didn't say given a solution to a differential equation, though that is the same thing. A family of curves may be a solution to a differential equation. It doesn't need to be. You could just specify some family of curves, like for instance, y equals c e to the, 7t. That's a family of curves. Like we just saw, well, I guess they're going to look different because they're going to go up like this for different values of c, and go down like this for different values of b. That's a family of curves. I never said that this was a solution to a differential equation. It's just some family of curves. This turns out to be a solution to a differential equation, but that's not, we don't really care about that right now. We're just saying, given a family of curves, an orthogonal, orthogonal trajectory is a curve that intersects each of the original given ones at a right angle. So here's a family of curves. X squared plus y squared equals k. So that family of curves looks like this. For different values of k, you get different circles, yeah? So there's your family of curves. Now we want an orthogonal trajectory. Well, that's an orthogonal trajectory because it's a curve. That thing itself is a curve. I know it doesn't curve, but remember curve just means, right? So it's a curve, and every time it intersects one of these guys, it does so at a right angle. And it doesn't matter, as long as this thing goes through the origin and is a straight line. Turns out that for this family of curves, orthogonal trajectories to it all have the form Cx, where C is some constant. You give me any constant, and this thing will intersect those at a right angle. How do we derive that? How could we possibly derive that? Which is, I think, is so cool. Like, I mean, it's like, you give me some family of curves, and we're gonna say, like, to me, when I hear that, and it intersects each one at a right angle, how can you guarantee that? That's interesting. Why did you come up with them one by one? You know, like I was doing here, right? We have a bunch of circles, and then it's like, well, I don't know, let's just try one. Does this work? I think so, and then you go through and figure, well, it turns out we could do this in one fell swoop. We could find a family of curves that has the property that we're looking for. I'm going to do that with an example here. So we're going to find the orthogonal trajectories all of them. We're going to find all of the orthogonal trajectories to this family of curves. Okay, here's the family. Y equals k x squared. So first off, let's just look at what that family looks like. If k is 0, is just 0. Okay, yeah, not interesting. If k is, say, 1, you have a parabola. It looks like this. If k is, say, 7, you have another parabola. He still goes through right here at the origin, but he's steeper, right? And so on and so forth. They get steeper and steeper for bigger values of k. When k is negative, they flip down like this. Right? But they still all go through the origin. Right? You might have a really flat one. Ooh, it does that. Right? But that is what that family of curves looks like. Maybe it's a solution to a differential equation. In fact, it is. I mean, you could just take the derivative of both sides. And that's a differential equation, right? Y prime equals 2kx. This is a differential equation. That's a solution to the differential equation. So, okay. So what we want is a family of curves. Some curve. I don't know what it's going to look like. Actually, but what I do know this, that no matter what it's doing, it's got to intersect here at right angles. Got to intersect here at a right angle. Got to intersect there at a right angle. This was one of them, right? The x-axis was one. When k equals 0, that's one, so he's got to go through like that. He's got to go through, he's got to touch like that. Now, I don't know. Well, yeah, because as these get steeper and steeper, they're going to have to approach like that. Anyway, we get something like this. I'm just thinking about if I had an orthogonal trajectory, we're going to make it so that he has to go through each one of these at a right angle. Something like that. Almost like a slope field is what we're creating here. But we can do this symbolically. Okay, it's going to look something like that. Don't say anything. Kind of looks like something that we might be able to guess. But we're not going to guess. We're going to do it. We're going to do it. What we're doing here is we're saying that this green function, whatever it is, it has to have the property that its derivative. You give me any point on the plane. You give me, say, this point on the plane. Then the derivative of the green one has to be at a right angle. It has to be perpendicular to the derivative of the black one. Okay? So every point on the plane, I think, has one of these curves going through it. And what I'm saying here is that the derivative of this guy, dy dx, has to be perpendicular dy dx of the green guy. So, can we use this to get black dy dx?
Yeah, y prime.
Yeah, just take the derivative, right? Dy dx is equal to what?
2kx.
2kx. Now it has to be the case that the green guy's dy dx is perpendicular. How do we get? Now this thing is a slope, right? What's a perpendicular slope?
-1 over.
Yeah, right. If you have some m and you want the perpendicular slope to it, you take -1 over whatever that original slope was. So dy dx that's perpendicular to it has to have the form -1 over the original dy dx, whatever that is. Right?
Yes.
So let's figure out what that is. That's -1 over this thing, 2kx. Okay, here's the problem. This assumes that you've selected one value of k, right? Whatever, so like in a sense, what you're doing right now is you're singling out this one solution right here with k, that k. This is maybe, I don't know, k equals 1, right? What we want is to simultaneously get all of them, not that particular one with that particular k. So what we're going to do is eliminate k from this. We just found that the dy dx that we want has this form right here, but we don't want a particular k. So what I'm going to do is say, well, hold up. Let's get that k by itself. K is equal to y over x squared, yeah? Right?
Yes.
From the original, it has to be that, it has to be. And so, I'm going to say, okay, that's negative 1 over 2 x. K now is y over x squared, because every one of these curves has to obey this. And so, every single curve has this property here, that k is always equal to y over x squared. So now we're done with k. K is gone. We can get rid of them completely. Well, let's just keep going here. This is the same thing as negative 1 over 2. One of those x's cancels, and we have y over x, which I could rewrite as the x goes into the numerator, y stays in the denominator, 2y, like that. Yeah?
Yes.
Okay, so let me get that up here. We have that the functions that we want, dy dx, have the form negative x over 2y. There's your differential equation, which describes what any one of these bad boys is going to look like. Is that separable?
Yes.
Yeah, okay, let's do it then. That's always your first question when you have a differential equation. Is it separable? Is it separable? Let me get this down here. This was y equals kx squared. That was my family of curves, the black ones. Now we want to get the green guys. And so we have dy dx equals negative x over 2y. Is it separable? You told me yes. I'm going to go ahead and separate it. We get 2y dy equals negative x dx. Looks separated to me. All our y's on one side, all our x's on another side. What do we do?
Integral.
Integrate with respect to y. Integrate with respect to x. And what do we get here?
Y squared
Y squared plus a constant.
equals negative 1/2 x.
Negative 1/2 x squared plus another constant. Now let's get our constants together. Get everybody else over here. We get, I'm going to bring him over here as 1/2 x squared plus y squared equals c2 minus c1. Or how about I just absorb all of those and make them a big C? X squared over 2 plus y squared equals c. What type of objects are these?
Ellipse.
They're ellipses. They are ellipses. And for different values of c, you're going to get different sizes of ellipses. You could see, another way you could see this, because this isn't the form that we're used to with these, but you get x squared over 2c plus y squared over c equals 1, which you could rewrite as x squared over root 2c squared plus y squared over root c squared equals 1, which means that these things go through at plus and minus 2c over here. So, no, plus and minus root 2c minus root 2c and root c up here and negative root c down there. Which actually looks like what we did, right? I mean, it does look like they're wider this way than that way. And so indeed, that's it. There are families of ellipses. I just think it's so. I just think it's cool graphically that you could like, cause that problem right there right? When you say, given a family of curves, so I'm imagining, okay, the plane is filled with curves, and every point on the plane there's some curve going through it. Okay, now find even just one. Find one function that goes through that every single one of those orthogonally. I'm thinking, you can't do that. That's ridiculous. How could you specify a function that goes through every single one of those infinitely many lines or infinitely many curves exactly orthogonally, exactly at a right angle? And then we find out that you not only can you do that, you can find infinitely many of them that work. That's pretty stinking cool as far as I'm concerned. And graphically it looks really cool. I suggest that you go to Wolfram Alpha. If you're watching at home, do this right now. But go to Wolfram Alpha, type this in, right? And it'll give you a slider for K. Then type this in, it'll give you a slider for C. And then just play with C and K and see what happens. And you'll see, like, yeah, it's pretty cool. And so this actually does have plenty of applications to physics. Lots of problems occur in perpendicular pairs. So like, for instance, the magnetic field is perpendicular to the electric field. So, electromagnetic field. There's a magnetic component that's always exactly perpendicular to the electric component is always exactly perpendicular to the magnetic component. And so your solutions end up having this, they turn out to be orthogonal trajectories. Other things too, like, there's something with heat flow. I don't remember. I don't know. I think your book says a bunch of examples. Here we go. Orthogonal trajectories occur in various branches of physics. For example, electrostatic field. In an electrostatic field, the lines of force are orthogonal to the lines of constant potential. Also, streamlines in aerodynamics and are orthogonal trajectories of velocity equipotential curves. Whatever. But there's lots of ways. I remember doing this in complex analysis all the time. It was always like, if we could find the family of orthogonal, orthogonal trajectories, then we'll have something we really care about. And so, yeah. I don't remember why. It was always, to me, it was always like, that looks really pretty, dude. Let's grab that. That's cool. Like, that's what I like. So, anyway, that's all I got for today. Good to go?
I think so.
Sure? Look like you're looking at something. Question?
No.
No? Okay, cool. All right, man.